trying to explain about the radio beam, but I'm afraid I don't know much about it.
Here comes one of our pilots. I know he'll be glad to explain it. Captain Butler, this is Mr. and Mrs. Cole.
How do you do?
How do you do? You folks enjoying your trip?
Oh, I think it's wonderful.
Oh, that's fine.
Captain, do you have time to explain the radio beam to Mrs. Cole?
Surely. We fly the highways of the air, Mrs. Cole, the same as you drive the highways on the ground. Ours is a highway of sound. That's why when you see pictures of airline pilots flying, they're always wearing earphones.
Oh, yes.
About 2 hours ago, we left Chicago here. We're headed for New York here. The Civil Aeronautics Authority maintains radio range stations along the route at frequent intervals, broadcasting a constant highway of sound, which we call the beam. As long as we're on this beam, we get a steady hum in our earphones. The moment we deviate in either direction, the signal breaks up into dots and dashes according to which side we're on. A long and a short if we get to the right, a short and a long if we're too far left.
Ah, if it were only that simple. Here's what the airways look like in the northwestern U.S. The airway that runs from Salt Lake to San Francisco and down to L.A. will be the one that we'll be working on in the next few videos. These airways are laid out using the four-course ranges as the pieces. If you look at this closer section, you can see the pieces that lead from Salt Lake towards Reno, and you might also notice that the legs on these ranges are not at exact right angles. Here's an old sectional showing the Elko Range, and it's 4 legs. There are only 4 legs on which you can fly, and when you're off to the left and right, as in the video, you hear an A or an N. Depending on the age of the sectional, the A and N may be explicitly marked on the chart, or the solid line on the side of the beam is the N side. So the east leg has an inbound bearing of 219 magnetic, and the west leg has an inbound bearing of 050 magnetic. The two strange-shaped things across the beams, marked Deeth and Carlin, are fan markers. Here's a DC-3 cockpit as I remember as a child sitting in the jump seat. This is the view I got. These are the coffee grinder receivers that we use to receive the range stations. I have a vivid memory of these as a child. They were labeled the red ADF and the green ADF, red for the left and green for the right. You had to tune the station with a crank under the scale. That's why they were called coffee grinder receivers. You'd turn that crank until the frequency that you wanted was in the scale. Then you had to listen to the ident, make sure you were tuned to the right station. It was the late 1920s when the four-course range was invented. How do these work? Here's a simple dipole antenna operating at a frequency below the AM broadcast band. It broadcasts almost omnidirectionally. The two crossed antennas of the range are loops. They broadcast at right angles to the wires and not in the directions of the wires. One of the loops is fed with an A signal, the other loop is fed with an N signal. The A and the N are complementary. One is dot dash, the other is dash dot. If the two are overlaid, you get a steady tone. Viewed from the top, you can see how these two crossed loop antennas will provide a steady tone in 4 directions. The legs are formed when the signal from the A loop and the signal from the N loop are equal. Nominally, this would be 45 degrees away from the direction of the loop, but that can be adjusted to make those legs not exactly 90 degrees apart. What does this mean to the pilot? While you're flying along the leg on the beam, you'll get a steady tone. Actually, you'll hear some clicking sounds as it switches between the A and the N side, but they'll have the same volume and they'll sound like a steady tone. If you drift off to one side, you'll start to hear one or the other tone. That's called the twilight zone. And as you get farther to the right or the left, you'll hear the A or the N, depending. And eventually, when you get way off course, you'll hear almost only the A or the N. One other very important characteristic of these stations is, as you overfly the range station, you will get a fade out of the signal. If you really hit it right, it'll almost go to nothing. This is the cone of silence. Since it's a cone, it's small at low altitudes and much larger at higher altitudes above the station. Okay, let's take a listen to what this is like. Right now we're in the middle of the N quadrant, so it's almost all N. When you hear the ident, you'll hear the N side being done first, and then the A side after that. Idents are done every 30 seconds. Now we're in the middle of the A quadrant. Notice on the ident that the N side is soft and the A side, the second one, is loud. Here we're just barely off course on the N side, in the N twilight zone. And now we're just off course on the A side, in the A twilight zone. And now, on the beam. A very subtle N, and now a very subtle A. Now we're still climbing out of Delta. We're going to fly across the range station to hear the cone of silence. You can hear we're on the N side, although the map shows us to the A side. That's just the difference in the georeferencing of the map. We came in on the N side and we exited on the A side, but since it went completely silent, we did pass over the cone of silence. If you miss the station, you'll hear it as a sudden change from A to N. This all sounds great in theory, but in reality, you have all kinds of issues, especially with these low-frequency ranges, that can affect their accuracy. Mountains, bodies of water, other variations of ground conductivity, mineral deposits, all sorts of things can bend the beams. Reflections off of mountains can also cause multiple beams. Changes in ionospheric conditions can cause swinging beams and shifting beams. To keep things in perspective, if you've done 100 or more ILS or VOR approaches, or even flown along the airways with VOR, you've seen this stuff also. It's a result of signals bouncing off mountains or buildings, and the FAA tries to do their best to site these facilities to prevent that, but under atmospheric conditions and whatever, it will happen. So besides having to figure out how much you need to crab one way or the other to compensate for winds aloft, you have all these other issues, especially with low-freq ranges, that can get you as a pilot. Here's an IFR en route chart from the old days, probably not the 1930s, more like the late 1940s or early 50s. Besides the 4-course ranges, you can see there's an NDB at Promontory Point. That's new. Also, the facilities have 3-letter identifications. You can see the fan markers and the various airways, red, green, amber, and blue. And you can see at the bottom, that's the Salt Lake area. And after we get familiar with how it sounds and how to maneuver around these range stations, we'll be doing an instrument approach, holding, and other things around the Salt Lake City area. I've made these historical IFR charts, sectionals, and approach plates available on the xplane.org site. There's a link below this video to the xplane.org place where you can download this stuff. In the next video, we'll take the old DC-3 up from the Delta airport and maneuver around the Delta range so you can hear what this sounds like in real time and get a better feel for it than just the snippets that I provided you earlier in this video. Hope you'll tune in for that one. Take care. Thanks.